Okay guys, in this video we're going to talk about two very special logarithms. Some logarithms that are so special that we give them their own names, as a matter of fact. And so we're going to start with the common logarithm. And we say that the logarithm with a base of 10 is just simply referred to as our common log. So you notice I say it may be written as either log base 10 of x or simply as log of x, but we assume when we write log of x that the base is 10. So the thing that we want to have as a takeaway here is that the common log, which is the log of x, is the same thing as the log base 10 of x. It's just that we tend to not write the base here. Kind of like when we take the square root of something, we don't write a 2 on the outside to indicate it's a square root. It is just by default that thing. So whenever we see just log of something, we're going to assume base 10. Okay, and so as we look at these right here, it says use a calculator to evaluate the function given by y equals log of x at each value of x to 4 decimal places, and then verify our results. What we're really looking at then is just evaluating this function at these 4 values. So for letter A here, I just want to show you that this is simply all we're doing. We're saying let's go plug in 100 for x and evaluate this. Well, the thing you got to keep in mind is if we were doing the rewriting method, you might be a little confused because you don't see a base there. But again, this is why we're talking about this particular log, because we want to assume that the base is 10. And in this case, we would get 10 to the y equals 100 if and only if y equals 2. Now what I want to make sure we can do is evaluate this on our graphing calculators. And so that's what we're going to take a look at next. Make sure that we get a 2. And then make sure we can evaluate for these right here. So the button that I want everybody to look for is your log or your common log button. And that is going to be located on the left column of your calculator. So as we look for our common log key, you're going to notice that we have this common log key right here. If you hit log of 100, in parentheses here, what it's going to tell us is 2. But in other words, 2 is the exponent that we could raise 10 to the power of to get 100. And so our value there would be 2. Now with respect to the rest of these, we do need to plug them in, evaluate on your calculator, but that's going to be as easy as just plug them in and write what you get as an answer. So for instance, if we wanted to evaluate y equals log of x at 1/5, this would be on letter B here, we would have, let's switch colors, y equals log of 1/5. In other words, what could we take 10 to the power of to get a fifth? And so as we do this here, I'd say log of 1 divided by 5. Ooh, try again. Log of 1 divided by 5. We get negative 0.69897. And so when it comes to logarithmic values and being accurate with, say, exponents, we always want to go out to 4 non-zero place values if helpful. So in this case, if I'm ending at this 9 right here, this 7 would say I round the 9 up to become a 10. And if that rounds up to become a 10, that makes this 8 next door to it a 9 followed by 0. So 0.6990, and it's approximately 6990, and it's negative. So we would get this value here, and that would be the exponent we could raise 10 to the power of to get a value of a fifth. As we look at this next one here, switching colors again, y equals the common log of 3.25. This is like asking, hey, what could I take 10 to the power of to get 3.25? So looking at our calculator here, we say the log of 3.25. It seems that we'd have to raise it to the 0.5119, so approximately 0.5119. And then the last one here, if we said, well, what would happen if I took log of negative 4 here? Now this is one of my favorites, because what we're really saying then is that we took 10 to the power of something and got negative 4, which I hope you realize right off the bat is not possible. So one thing to keep in mind is going to be this. We can never take the log of a negative value, because that's like saying we took some positive base to a power, and when I multiplied it by itself that many times, I got a negative output. So one thing that we want to make sure that we note here is this. We cannot take the log of a negative, since a positive base to some power must come out to be positive. So as we get to graphing these in upcoming videos here, we're going to notice really quickly that our domain is only positive x values that we can plug into these functions here. So what's the takeaway from this video? Well, remember that the common log is what we call it, and the common log is any log where we don't write the base, we just assume that it's base 10. Okay. So our other very important log is going to be what we refer to as our natural logarithmic function. So we have our common log and we have our natural log. It says in the previous section we explored the graph of the natural exponential function. This was y equals e to the x that had a base of e. So that Euler number there, this is a very common base we use, especially when we model things with exponential growth and decay. And so it is fair to say that we do want to define this function as well with a base of e. So when we see this function defined by y equals log base e of x, what I want you to know is that we often write ln of x. And so what we're going to do is we're going to make sure we write a little note here. The natural log is the log base e of an input, and we will always write that as the ln of x. And so we read this as the ln of x, but we could also read this as the natural log of x, okay? And so don't ask me why they didn't call this the NL, the natural log, but it is the ln, and when we read this right here, we want to just assume that the ln of x means the same thing as log base e of x, okay? So we're going to use the ln button on our calculator to evaluate these right here, but first thing I want to do is I want to make sure that we evaluate, and so actually show our work. It looks like we want to find y equals the ln of 73.25 for this one right here. So very first thing I want to do is rewrite this exponentially. And again, I start at my base and I hop across the equal sign and come back again, except for we have to know that this base here in this case is e, which is about 2.718. So we're asking, what could I raise e to the power of to get 73.25? So grabbing our calculator here, you're going to notice that your natural log key is just below your common log key. So the natural log of 73.35 is equal to about 4.2952. So about 4.2952. So one thing I want to show you here is if we take e to the power of about 4.2952, we're going to get approximately what we started with here, which was 73.25. And why didn't we get exactly what we started with? Because when I put the exponent back in, I only put in the rounded off to 4 places. And so you can see that even rounding to the 4th spot right here, if I plug that back in, it still doesn't get me exactly back to what I started with here, which was 73.35. It just gets really close to that, 73.35-ish. So in terms of going out to 4 decimal places that aren't equal to 0, non-zero decimal places, that's why it's important that we do that. So really quickly here, let's go ahead and evaluate these. We would say y equals the ln of 0.4. So e to the what equals 0.4. We can ask our calculator here. So we say, just simply put, the ln of 0.4 is about negative 0.9162. So about negative 0.9162 would be the exponent there. And then this one here, as you might suspect, y equals the ln of negative 2. This is bad news bears. We say that it does not exist. It is not possible, just because if you said e to the y power equals negative 2, that wouldn't be a possible thing. So let's go ahead and try to take the ln of negative 2, and I just want you to see that it's going to give you a non-real answer. Okay, so with respect to 2 very special logs, we have our common log, base 10, and our natural log, base e, and we're going to be using those very, very often. Cheers.